Hello everyone, in today's video we are discussing about voltage to current converter. So when we are using the voltage to current converter, whenever some devices requires the output in current only but our device is giving voltage, at that time we'll use the voltage to current converter. See, in most cases, as we know that the measuring device in the form of voltage. So we need output in current, that time we'll use this conversion method. For example, we have a sensor. So this sensor will give the voltage as a output in display. But what happened? This voltage will degrade or corrupted, which will get corrupted across the cable. See, here we have written, due to wire impedance and addition of noise, output voltage may get corrupted. That corrupted output we cannot send as a display output because it will be not given as a accurate value. So we'll convert voltage to proportional current. So when we are sending from sensor voltage and we are converting that voltage to current, the display will be accurate. Whatever sensor is giving, that is only displayed in the output. So we can say sensor is giving the current, and even though it is in moving from sensor to till display, from source to destination, there is no corruption of the current. There is two type of conversion. First one is voltage to current converter using floating load, and second one is voltage to current converter with grounded load. So we have two conversion. So here we have voltage to current converter with the floating load. So with floating load means what we have done, we have given the load to the negative, that is inverting terminal, which is not connected directly to the ground. So here we are sending some resistor 1 current 1 to the input, but it is not going directly to op amp. It is connected to load, which is a voltage follower. So here V in, that is input signal, is given to the non-inverting terminal. Voltage feedback is given at inverting terminal, which is virtually short circuit. So this is virtually short circuit point, will say. So load is connected to the op amp and the registers. So here this point is called as a virtually short circuit. So as it is virtually short circuit, we can consider that V in input is equals to V in at the inverting terminal. Okay. Now by applying KCL, so by applying KCL, we'll get as current at load is equals to current passing at this resistor 1, because here we not flowing any in op amp, there is no flow of current, so we can take it as 0. So V in will get as, V in is nothing but, so inverting terminal is equals to non-inverting terminal, so we will take the current flowing at load. So V in is nothing but current flowing at load, will get current flowing at load with resistor load. So we can, so this part where we took, so IL is equals to V in divided by RL. So this is our conversion of voltage to current. Next we have ground load to voltage to current converter. That means we have given the load directly connected to the ground where the input is given. So we have given in previous also, we gave the input for the non-inverting terminal. Here also we are giving input to the non-inverting terminal, but what we have done previously, we were connecting it to the inverting terminal by giving the load connection, but here we are connecting directly to the input signal. So before starting, we can say that here RF is equals to R is equals to R1, which will give us as, which is nothing but equals to R, and we can assume R is equals to 1. Okay, we can assume it as R is equals to 1. To find voltage, so voltage So we can say voltage output across inverting terminal we get V0 into 1 plus Rf divided by R1 so we'll get into V1, which is nothing but we'll get 1 plus R divided by R into V1, so we'll get 1 plus 1 1 to V1, which will give us 2. V1 has V0 value, and applying KCL we know that I1 plus I2 is equals to current flowing. So the sum of two currents flowing at non-inverting terminal when there is applied a current. So now we can get, so where I1 is flowing, so this here I1 is flowing, here I2 is flowing. So I1 is flowing from V into V1, so I1 is nothing but V into V1, because this is a short circuit point, virtual short circuit point, whole divided by this all resistor, we can call it as R, and we'll get I2 equals to, I2 is flowing from V1 to V0. Yes, we are getting from V0 minus V1 whole divided by R. So place this equation in KCL. Put I1 and I2 value in IL equals to I1 plus I2. We'll get IL is equals to V in minus V1 whole divided by R plus V0 minus V1 whole divided by R. So we get IL into R equals to V in plus V0 minus 2V1, which will give us R. So this R we have sent here. So we'll get V in plus 2V1 minus 2V1 IL, yes, we'll get into R. So this will cancel, so this will cancel, so we'll get 2V1 into current flowing at resistor R similar, so IL is equals to Vn by R. We'll get Vn by R. So these two are common, we are cancelling it. Similarly, like floating load, we'll get the current. So this is our final equation.